Alright, welcome to another podcast. In this episode we're going to be taking a look at partial fractions again, although this time it's going to be a little bit different. Let's start off by looking at our integral that we have, and in doing so I'm going to need to factor the bottom. That should always be your first step if the bottom is not factored completely. And so in order to factor the bottom, I'm going to pull out an x squared, and then that will leave me with an x plus 2. Now, a couple of things that we're looking at here. The first thing that jumps out to me is the x squared. The x squared is an example of what's called a repeated linear factor. So this is an example of how to do partial fractions when you have repeated linear factors. The decomposition that we're going to propose here looks like the following. So I'm going to take my fraction. We'll come back to the integral later. I'm going to take my fraction and write the following decomposition. We need to have x squared, and we also need to have x plus 2. Now let's deal with the x squared first. Because this is a degree 2 polynomial, the most general numerator would be a degree 1 polynomial. A degree 1 polynomial is a linear equation. So that's the most general top that I can give that fraction and still keep it proper. Here, because this is linear, the most general top would be this. Now, this is generally not the form that we use, and it's not the form I used in class, because we do one more step. Notice that I can take this ax plus b over x squared and write it in two different ways. I can take ax over x squared, and then I can take b over x squared. And I still have my c for the decomposition there. Well, what you immediately notice is that the x's cancel out with the a, and so you're left with a over x for the first piece and b over x squared for the second piece. And this is like the decomposition that we used in class. The one thing I want to point out is that because this is a repeated linear factor, it repeats as many times as it has degree. Because it's an x squared, there's two repeats, one for each power of the denominator. So this is the decomposition that we want to use, and so we're going to have to find values of a, b, and c. Now, our cover-up technique will only work if the factors involved are at their fullest powers, meaning that I can use cover-up to find b because its denominator is at full power x squared, whereas this one is not, and I can use it to find c. So let's take a look at those. In order to find b, b would be the limit as x goes to 0 of x squared, the full factor, times the fraction itself. And then I'm going to divide through by the denominator here. Go ahead and do our cancellation, and then take the limit and evaluate at 0. And if you evaluate at 0, you should get negative 2 over 2 or negative 1. So that means the value of b is negative 1. Alright, if we do the same thing for c, c is the limit as x goes to negative 2 of x plus 2 times this fraction. And now we get the x plus 2 to cancel instead. And then if we evaluate everything that's left at negative 2, we'll get 12 on the top and 4 on the bottom. So the value of c is 3. Now notice at this point we've recovered 2 of the 3 constants that we needed. There's no way for us to do cover-up with a, the reason being quite simple. If I multiply by x here, that's not enough to cancel the x squared in the denominator, and so evaluating that limit at 0, I'd still have a 0 in the denominator. We showed that in class. So the question is, how can I find a? Well, in order to find a, you're basically going to plug in values for x. Now, the simplest value to plug in for x is one that you haven't considered in your limits so far. So my two limits were 0 and negative 2. I haven't done a limit as x goes to 1, so if I plug 1 on both sides, I should be okay. if I plug 1 into this side first, then that gives me 5 times 1 squared plus 3 times 1 minus 2 over 1 squared 1 plus 2. And that should be equal to what I have over here on the right hand side for my decomposition. That's a over 1 plus, remember b now is negative 1, so negative 1 over 1 plus 3, c is now 3, over 3. If we clean this up a little bit, this is the same thing as saying we're going to have on one side we're going to have 6. So if you add the top over here, that's going to be 6, and if you add the bottom, that's 3. So 6 over 3 is equal to, the right hand side here is a minus 1 plus 1. Well, those obviously cancel, and so that says a is 6 over 3, or a is 2. So knowing that a is 2 completes our decomposition. I have all 3 coefficients determined, which means if I return back to my original integral, this is now the integral of 2 over x minus 1 over x squared plus 3 over x plus 2. And I can do the integration piecewise here. The integral of 2 over x is 2 natural log of x. This integral is just a simple power rule. X squared means that you're going to take x to the negative 1 and divide by negative 1, canceling the negative that we already have. And so a little power rule there will make negative 1 over x squared 1 over x. And then finally, the 3 over x plus 2 is 3 natural log x plus 2. And so the whole point here was we took that original integral, which was pretty complicated as was, and we broke it up using this idea of creating proper partial fractions. We had to repeat our linear factors. We could do cover-up on the ones that had the highest powers in the denominator for their respective factors. And then we used just the fact that this is an equation here to plug in values on both sides to recover the coefficient a that we didn't know. All right, we're going to take a look at one more partial fractions podcast after this, but this is the second of 3, and thank you for watching.